Okay, so this is what I have to say about the system bus. So we have address, data, and control. These are the categories. There might be other considerations into this, but for now we're going to deal with it as a bunch of wires to connect the different types of components. So the third and last component that I want to talk about today is actually the central processing unit, or the CPU. And again, it's a very simplistic overview of it, but I want to think about it as three components as well inside the CPU. And these components are the arithmetic and logic unit, or the ALU. It has some registers, general purpose and dedicated register for certain functions, and the control unit. So let's start with the arithmetic and logic unit. This is something you have probably seen components of in digital logic. So an arithmetic and logic unit usually can, as the name implies, can actually perform arithmetic operations, kind of like addition, subtraction. We're using signed or unsigned. And my recommendation, if these are a little bit unfamiliar to you, that you need to actually review how do you do signed and unsigned binary operations, kind of like addition and subtraction. The PIC18F as well can actually do unsigned multiplication. It can actually do multiply just for the unsigned version. It will not be able natively, or the ALU, the arithmetic logic unit in the 18F, cannot do any signed multiplication or signed and unsigned. Actually, not only signed and unsigned, it cannot actually do any division whatsoever. So it's only capable of doing unsigned multiplication. Now, this is what I mean by incapable is it's natively, the arithmetic logic unit doesn't have any circuitry to do signed multiplication or any division whatsoever. However, we can manually write some programs and some algorithms to actually do the multiplication and the division, and we might get to it towards the end of the course, but I just want you to keep that in mind. So, and these are in regards of the arithmetic. There's other arithmetic operations. For example, you can do find the ones complement. Another thing you can do, shift or rotate registers. And if you guys remember, shifting can sometimes means that, especially if you're doing arithmetic shift, shift by left or shift to right, is you're dividing by 2, multiplying by 2. Again, if this is a little bit unfamiliar to you, refer to what shifting and rotating are, okay, from digital logic. And lastly, it's also a logic unit. It's not only can it do arithmetic operations, it can also do logic operations. And what I mean by logic operations, like AND or XORs and so forth. So you can do all of these. So an ALU has several components in it. You have seen these components in previous courses. You might not have seen all of them, but you have seen at least a majority of them, and they're connected somehow, and they're controlled. They're controlled to form some sort of an operation. So arithmetic, all logic unit or whatnot, they all need some sort of a data to operate on, and the data can actually be stored. Definitely can be stored in the memory that we talked about, the data memory. But usually you can see the CPU have some sort of an internal registers, and that will make its life a little bit easier. It shouldn't be required to go to the data, bring some data in, and operate on it, and come back to it. These are actually costly. So you can see that the CPU has some sort of an internal register structure that will get the data in, operate on the data, and then spit the data out and save it in the data memory and so forth. This is for general purpose, but also it has some sort of a dedicated register that have very, very specific functionalities. For example, the instruction register, the program counter, and so forth. So I'm gonna go through these very, very quickly. So an instruction register is just a register that does the following. You're operating a program, so you write your program. You're going to see that it actually lives in the program memory, and you can see in program memory that I have these particular data in here. It's basically, and again, 0x, not again, actually, just in case you don't know, 0x I'm now referring to it as hexadecimal. So this is 1, 2 in hexadecimal, this is 0e in hexadecimal. The same goes with the address in here. So I have a program memory, and that program memory is actually arranged somehow. And in this particular cases, I basically arranged it as bytes. So you can see that this is 2 hexadecimal digits. That means I have an 8-bit total. Again, if these are unfamiliar to you, please do refer to your digital logic course so that you can actually remember what I'm talking about. This is the conversion between binary and hexadecimal. Anyway, so I have a byte in here and a byte in here. So this is basically this is basically, from program perspective, these are 16 bits, so the 0E and the 1, 2, they are an instruction. So when the processor is trying to do its own thing, it will read the 0E and 1, 2, whatever that means. For now, we don't care what that means, but we will later. we'll be writing programs, and these programs will be interpreted into these particular patterns of zeros and ones. So the instruction register's functionality is actually the CPU is going to issue some sort of a read operations or fetch, that's what we call it. So we're going to read an operation from the memory, it's going to bring it in here, and it will save that particular value, which is 16-bit, it's going to save it as 0E12 in the instruction register. And then the CPU will go and interpret its meaning and do its operation on it. Okay, so other registers, there are many of them. These are just some of the most common ones you can find in most microcontroller units is the program counter, and this is actually a really interesting one. It's just a counter, kind of like the counters you've encountered in digital logic. It's a counter, and its purpose is to tell me where I am in the program. For example, if I am reading this particular value in here, the program counter component will have this particular value, which is 0042 inside it. So the program counter tells me what is the address of the next instruction to be implemented or to be executed. For example, if I'm reading this, I will go through and I read this address and I read this address, and then the program counter will save inside it that my next operation is going to be stored at 0044. So some of you might think, well, if I'm reading a program, isn't the program just written sequentially, basically one cell after the other, one cell after the other? And the answer is, generally speaking, yes, the program is written sequentially. However, sometimes these instructions might lead you to a jump, and that jump could be, think about when you wrote in C, you wrote some sort of a function and then you called it from main, and what you did is you jumped to that function, you did your own things, and you came back, and it's the same exact thing. This is, frankly speaking, you were changing the program counter in your computer, in your processor. So the program counter might be operating on certain things, and then it jumps later, and then from this jump it continues and then comes back and so forth, and we'll get back to this towards maybe the end of this particular part of the course. All right, so memory address register, it's a register that contains an address, and that address is actually the address that the CPU is interested in terms of data memory. So it might have some sort of an address that says, hey, I want to read FA1, and that means I'm interested in the location FA1 inside that data memory, and I want to read it. So, and it stores it internally in memory address, so that if an operation wants to save into that particular memory location or read from it, it can directly get to it. It doesn't have to generate the address and get to it and do that. Okay, an accumulator is one of the most important actually registers, and it's actually very functional registers, sometimes referred to it as A. In PIC 18F documentation, you will see it as a working register or WREG, and some microcontrollers are accumulator-based microcontrollers, others are not only microcontrollers, processors in general. An accumulator is a place where if you're doing an operations, for example, you're adding a couple numbers, it stores it in it, and then after it finishes, it actually throws it back to memory. So it's a very useful, or it's kind of like a working thing, kind of like you're looking at that data point now, and you're dealing with it now, and then you're going to throw it and do something else with it with that data later, and because you want to deal with something else, and that's basically what we call the accumulator. So general purpose registers, a lot of microcontrollers or processors have general purpose registers. Registers, generally speaking, are a lot faster than memory. You don't have to. They're a lot faster than memory, but they take some of the CPU physical space. So the chip gets bigger when you actually put register. This is very simplistic overview. It doesn't only take some space from the CPU, it also takes some power. So usually I can think about them as expensive, and expensive means a lot of things, but expensive in terms of power, expensive in terms of production, expensive in terms of space. Registers are usually expensive. So if you're putting a register inside the CPU, that means you really need it. So it either has a certain functionality or really need your processor to be faster. So general purpose ones are registers that just let the processor do something a lot faster. So you might be doing something and the processor goes to the memory, read something and put it in a general purpose register for the next instruction so that it's ready to do it. So a general purpose register will help you do that. And we're going to be learning more about a general purpose register, because we're going to be writing some sort of an intermediary operations into it while we're doing it before we actually throw it and save it in the data memory. Okay. An index register, you can think about this index register. Actually, it saves the index of an array. So think about C arrays, the one that you had to deal with. So it helps me by telling me which element of the array I'm in and whatnot. And we'll get back to it when we talk about example. Status register is also very important. A status register is just a very, very special register that has a bunch of bits in it. Well, like any other register, so it has a bunch of bits, but each bit carries significant information. So if you read this particular bit in here and I say that it's 1, it's actually a flag that something has happened. I drew it next to the status, to the index register. I should probably do it next to the status register. So a status register is here. It actually has several locations, and each one of these locations carry a significant meaning. So if I actually tell you this particular location in the status register, this particular bit of the status register is 1, that means I'm telling you there's a flag that has been risen. Some of these flags, or some example of these flags, is a carry flag. So if you guys remember, you add a couple of numbers and then you have something we call the carry out. Okay, and if your carry out was 1, you're going to see that that particular bit will be asserted to 1. Another example of a status register is what we call a 0 flag. And a 0 flag tells me like you've just done an operation and that operation resulted in a 0. You're going to see that that flag will actually be 0, or will be 1, to tell me that the result was 0. There are other flags. Some flags are sign flag, for example. If I did an operation in the CPU and the operation resulted in a negative number, you're going to see that that negative flag tells me, hey, I got a negative number. There's overflow. There's other status register, and they're very important not only in knowing the status of what's happening right now, but sometimes we're gonna be writing some sort of a jump, or you can think about it as for loops or something like that, and they are based on the 0, that the previous result resulted in 0. If so, do so and so. Okay, kind of like conditional and jumps. We'll talk about this when we talk about assembly language programming and C programming. And the last one is the stack pointer register. It actually deals with something we call a stack, and I'll give you an example towards the end of the section to actually explain what it does, and it's actually really important. It saves an address similar to the program counter. It saves an address to something, and we'll get back to it when we talk about the example. Okay, so to recap, what we have seen is a central processing unit have an arithmetic and logic unit, or something we call an ALU, and that arithmetic and logic unit does arithmetic and logic operations, like the name implies, and we have some registers. Some of them are very specific. They have specific functionalities. The last element I want to talk about is a control unit, and it's actually a really interesting part of the really interesting part of the CPU. And it turns out to be that all these operations that we do, whether you want to read from memory, or whether you want to add a couple of things, or whether you're going to extract something from memory, get it back in here, extract another value, get it back in here, add them, subtract them, do the result over there. These are just sequential steps that you need some sort of person to actually tell you, like, what do I need to do right now? For the processor, that would be the control unit. So the control unit is a unit that tells the processor, or guide the processor through the step of performing certain operations, and there are many operations. And you can think about this particular control unit as a finite state machine, or an FSM. Yep, again referring to the digital logic. So you can think about it as, well, in order for you to actually add a couple of numbers, you need to go first to the first state, which is fetch the first value from certain location, and then the second state, which is fetch the second value, then the third state, send it to the ALU in a certain location, then the fourth state, tell the ALU to add, and the second state, like take the value that the ALU gave you somewhere, and then you come back, and so forth. You have seen this when we talked about finite state machine. You can think about the control unit, or one of the major views. It's more complicated than that, but I usually think of a control unit as a finite state machine, more or less. There's other ways to create control units, but I usually like to think about it as, in a wired way, it's actually a finite state machine. And it's not only that simple, it's actually more complicated because it controls so many things. But the purpose of that control unit is actually, it is usually connected to the it's connected to the system bus. If you guys remember in here, it's connected to the system bus. It actually tells the memory that the address on the address lines are ready and the data is ready to receive it. You go and read or write, and actually controls it. So usually the control unit is connected to all these control signals, and it asserts them or deasserts them or do something like that. Okay. All right, so what I want to do today is I want to stop right here. I'm going to stop at this particular part and the summary of what I want you to see is the following. So what we talked about is we talked about the PIC-18F, and in the PIC-18F I have three major components. I have the CPU, I have the I/O, and I have the memory. And in the memory, particularly in the 18F, you're going to see that we have program memory and data memory because PIC-18F follows a Harvard architecture, and all of them are connected by system bus. Okay. All right. So now what I want to do is I want to show you how these basic components of a microcontroller or a microcomputer actually interact with each other by going through a simple example program. So the simple example program I'm going to show you is these two particular instructions, or operational codes, or opcodes, that's what we call them. And they do a few things. We're going to go through the details of this particular program. This particular example program could be part of a much bigger program, okay? And what I'm showing you in here is how would that program actually, or that part of the program actually interact with the different parts or different components or different units that we've seen. So what I'm showing you here is I'm showing you the memory. Specifically, I'm showing you the program memory and the data memory, and I'm showing you some of the CPU registers, not all of them, but whatever is relevant for this particular program. There are a lot more and things are changing in them, but I just wanted to show you an example of what's happening. Of course, there's a lot more detail. For example, there's a system bus that should go in here. There are the I/O units but this particular program doesn't deal with it, so we're not going to include them for the sake of simplicity. What you can see is the following. So this particular program is saved in program memory. So what I did is I went in here and I saved this particular instruction, which is 0E07. And again, we're dealing with hexadecimals in here because they're easier to write. And then here 2641, and this basically here is 2641, and I save these particular two instructions in these particular two locations. These two locations, you're going to see that the difference between them is 2, because again, as it turns out to be, that the program memory is 16 bits. You can see that I have 4 hexadecimal digits, each one of them 4 times 4 is 16 bits. So I have 16 bits in here, and I have 16 bits in here. So the difference between them is 2 because I'm using byte addresses, not word addresses. If this particular concept is a little bit, if you didn't understand, or this particular concept was not very clear to you why we are having a difference, I want you to think about it as like I'm dealing with 2 bytes in here, so I need a couple of locations to actually save them, and I have a couple of bytes in here, so I have a couple of locations. So the next one here should be probably 14, okay, 00014 hex. If you still have problems understanding it, please place some sort of questions on Piazza so we can actually have a discussion about it. Also in this particular program, and for this particular program, because we're going to be using that particular location, I decided to put this particular value, which is 02 in hex, in this particular location. All right? Okay, so the content of the accumulator and the instruction register, at this particular moment it doesn't matter because this particular program doesn't care what happened before, or this particular part of the program doesn't happen. So I don't care what's happened. There are some information in here, but at this particular moment I don't care about them. But what I care about is the program counter, and you can see that the program counter actually saved this particular value. The program counter tells me your next instruction, or the address of your next instruction in the program memory is this. So what the program counter is telling me is your next instruction to be executed is located at this location 00010. Okay, and that particular instruction, we can read it in here now. So what the CPU does, or what the program does, I'm going to go through the steps of implementing it, and you're going to see what's happening. So the first step it does is the CPU tells me, you know what, I need to figure out what is that instruction that I need to execute. So the first thing it does, it goes to wherever that program counter is pointing to. It's pointing to this particular location. It reads or fetch that particular instruction and saves it in the instruction register. Okay, so let me show you that. So what happened right now is the CPU went and issued all sorts of control command using its control unit, using the buses. It put the correct address on the memory address here. It basically connected the data to the IR registers. It did some sort of a decoding and multiplexing and so forth to actually do that. There's a lot of details involved, but for now, what I really care about is that it brought that particular instruction and put it internally into instruction register. This way, the CPU can actually interpret that instruction register. And let's read the comment next to that instruction register. It tells me that you are loading the value 07 hex into the accumulator. So what it really does is the CPU is going to take that instruction and we're going to dissect it. And you're going to see that dissection later on. We're going to see how it dissects it. But pretty much, it's a program is a patterns of ones and zeros. the control unit within the CPU knows that 0E is just issues a command to load the accumulator, and the 07 is the value that will load it into. So you can see is it will go to the accumulator, it will put 0.7 or 07, not 0.7, 07 in here, and it will tell me I am ready. The program counter should refer to the second point in here. So that's exactly what happened in here. So you can see that I put 07 in the accumulator because this is what this instruction is telling me, and it's telling me that the program counter should now move on to the next location so that it can actually execute the next instruction. And that's exactly what's happening. So my program counter is pointing right now here. The accumulator value has changed. The instruction register has done its thing. So next comes, okay, well, I have another instruction. So what the CPU does, it follows the same thing. It goes to its control units and it tells it, you know what, there's a new instruction coming, please bring it and let's interpret it. So it goes in here, it goes to the program counter, is pointing in there, and it tells me I need 2641 as an instruction. So I'm going to read it, bring it back in here, and I'm going to put it inside the instruction register. So the instruction register now has the value 2641. The control unit for the CPU will go and try to dissect and interpret what this means. What this means is the following. Look at that. So I'm going to look at the note of what the program doing. It's adding, and let me just explain to you this particular notation that is used in the book. If you're reading the book, it's actually telling me whatever you put between brackets, it's the value stored within that thing. So in here, I'm telling you, go to the accumulator and give me the value stored in it. Pretty much I'm telling you, go to the whatever the A is pointing to, or whatever A contains, and it contains the value 07 in hex. And what the comment is telling me, this particular instruction, which is 2641, it's telling me go to, okay, it's telling me go to, okay, so I'm gonna have to write this one more time. It's gonna tell me that, hey, go to the A, you're gonna get that value 07, you're gonna go to the 0x41. This is basically, it's telling me go to memory location that is referred to by 41. Address 41 is here, and bring that value stored in that particular location, and that value is 02. So you're going to bring 02, and it happened that this particular instruction does the following. Come on, I don't know why it keeps doing this. Okay, gotta change my setup. Maybe for next lecture I'll change my setup to do it. So it's gonna go A. It's going to go bring 07. It's going to go the 0x41. It is actually going to bring the 02. And what this instruction is telling me is I want you to add that value, which is 07, and the value 02. And if you add them in hex, you're going to get 09. And you're going to store the result back in the same location where you got that 02. So you're going to go back in here and you're going to store 09. And of course, you're going to be losing the value 02. So this is what the 2641 mean. Now, the control unit of the CPU is what's going to interpret this. And the way we're going to write it as humans, we're going to see it with assembly. It's going to get interpreted this way. Later on, we're going to write this program. At this point, I don't care that you understand what these numbers mean. All I want you to know is the following. Now, the instruction register went to that particular location and brought it in. Now, the control unit within the CPU is going to dissect this and interpret it and does the action on it. So the first step it's going to do, it's going to go and get that value, brings it in here, sum it to the accumulator, and it's going to go back in here. And not only this, you're going to see that that's exactly what happened, but it tells me, well, I'm done executing this command. You need to move the program counter to the next location, and the next location is here, 014. And this way, you're going to see that the program actually continues executing as before, and so forth. So what I've showed you in this example is a few usages of these dedicated registers within the CPU. One is an accumulator, the other one is an instruction register, and the program counter. Other registers actually operate a little bit differently, okay, because they have different functionalities. Next, what I want to do is I want to give you another example, and that example is going to refer to the stack. So the stack is just what we call, at least in here, the one we're going to be dealing with is what we call, it's a LIFO, which is last in, first out buffer. Okay, it's just a bunch of memory that you can store certain things in it and then get it back from it. Let me explain to you why we need a stack and what's its application and how we use it. And we're going to see how we can actually store certain values into it and read certain values from it. So let's assume that we're executing some sort of a program, kind of like the program we just saw a few minutes ago. You can see that the program counter is pointing exactly where that red that red cell is. So the CPU is going to go there, interpret it, does its own thing, and the next step it's going to move the program counter to the next location, and it's going to do the same thing. It's going to fetch it, interpret it, take some action on it, and based on that action it's going to move the program counter again and again. And you can see that this is actually happening, but it just happened to be that this particular instruction that happened to be stored at the 14 location in address 14. It just happened to be, it's a call to another subroutine, kind of like what we did by calling some sort of function within C, within the main function of C. So if you're writing a main function and you wrote a call to another function to do something, you can see that what I'm effectively doing is I'm telling it, hey, your program counter, the next step is I'm not ready to execute location or instruction stored at location 16. What you need to do is you need to go, and I decided to store that subroutine or another function in here. You need to go over there, execute that, and then when you return, you continue. Kind of exactly the same as, or you can think about it in exactly the same way you wrote functions in C. You are writing a function, you call it, you do your own thing, and then you return. Okay, so the keyword is return. Okay, so what we need to do is we need to know where we're returning. All of these is happening under the hood for you when you're writing C, but when we're writing microcontrollers, you become a much more powerful programmer or application developer if you actually understand what's happening. What's really happening is the following. The following is happening is actually the CPU is going to say, well, my program counter is actually referring in here. It's at this particular location. So what I'm going to do is I'm going to save that location. So I'm going to save that location, and the place where I'm going to save it is actually what we're going to call a stack. Okay, and then I'm going to jump. I'm not going to go to the 016. I might jump way further. I just want to save slide space. I'm going to jump in here. I'm going to do my thing with the subroutine. Okay, you're going to see that the program counter content has changed to refer to this particular thing because this is what I'm executing at this point. And then I'm going to go to another location, and let's assume that for some reason or another, that subroutine is really small and it just consists of these particular two instructions. And the second instruction is where I'm returning. So now the program or the subroutine is finished. It wants to return to the place that it was in. If I didn't have that stack value in here, I wouldn't know where to return to. And this is why we need a stack. Okay, so what happened is now I know that I'm returning, so the CPU is going to go to the stack and it tells it, what am I supposed to return? It's going to tell it, you return, this is where you left off. And you continue executing the program from there. So you can see now the stack is empty, or it's empty. Why do I need a stack? Because I might have not only one jump, but I might have several jumps. Okay, I might have a jump, and then that subroutine is calling another jump, and then that subroutine is calling another jump, and the subroutine is calling another jump. So what I'm going to be doing is not only am I going to be saving, for example, the 0, like let's, for the sake of simplicity, I'm not only going to be saving the 14, for example, I might be saving the 102, and I might be saving then the 107, or so forth. And every single time I'm returning, I'm going to return to the previous step. So, and every single time I return, I will actually just delete that value in here, and then go in here, and then delete this value in here, and go in here, and so forth. So the reason why we use a stack is because I do care about several jumps. And it turns out to be that in PIC 18F, you can actually do, I think, 32 jumps total, because the stack size is actually 32 lines, okay? All right. So the process of putting data into stack or getting that data out of stack is what we call a push a new data into a stack, or pop a data from the stack. So I'm going to give you an example of how that actually works and how generally it works. So this actually refers to the stack pointer register. So if you go back, and I told you I'm going to explain it to you with an example. Let's just see. So you're going to see that the CPU registers that are here. Okay, so these are examples of the CPU registers. What I did is I told you I'm going to give an example with the stack pointer register, which is the SP register, with an example, and that's exactly what I'm doing right now. So this is the purpose of the stack pointer register. Okay, so we go back in here. Let me just see if I can actually jump faster to it. The way I'm going to do a push, here's a push. All right. So you're going to see that what I'm going to be doing is here. Again, so I'm going to explain it to you with an example similar to what we did a few minutes ago for the program. So you can see that I have that stack pointer register, and I have a value or a new value I want to push into it, a new address place, or in the program memory, the address, these values that we just pushed, and I want to push into it. So in what we have also the stack. So what I want you to see is the following. The stack has these particular values. These are actually the values of the jumps and how do I get back to it. Now, of course, the stack has different usages, but this is just one of them. It's just to save where I need to return to. So the last value or the last jump happened from this particular location, and now I'm executing my program, and then if I need, let's assume that program happened or the subroutine happened to jump to another location, and that location happened to be, or the location where I'm jumping from is here. So what I need to do is I need to save that particular value here. What you're going to see is the stack pointer actually does the following. The stack pointer has the value or the address within the stack of the last element that I was actually dealing with. So the last element, and this is why I highlighted it in red. So because it has CO4, so this is location CO4, that tells me that the last element you pushed into the stack is this particular value in its location located at CO4. Now, if I want to push this new value into the stack, what I need to do is I need to actually issue certain commands, but it's most simplistic view is actually, I'm going to push that previous value here. You see that 1AB3, I'm going to put 1BA3 in here, and I'm going to move the stack pointer one more. So the stack pointer tells me this is the last value. So the last jump happened from here. Okay. Again, if I have another value that I want to push, what it does, it does the following. It writes it at this particular location, and the stack pointer now points to it. So the stack pointer technically is pointing to the bottom of the stack. Certain stacks deal with the top. I'm not going to confuse you with it. This is how at least PIC18F works. So it actually points to the bottom of the stack, which is the last element in the stack. So the last element in the stack, we call it the last input. It is the first one that gets out, is the first output. Okay, this is why we call it the LIFO buffer sometimes. Okay, so the stack is a type of a LIFO buffer. So last in, first out. Now the last jump happened in here. I'm doing my own subroutine, and now I want to go back to wherever I jumped from last time. So what I'm going to do is I'm going to read that value in here. It's actually at the tip or at the bottom of the stack where the stack pointer register is pointing to. So the stack pointer register is telling me I'm here. So, and I want something, the reading a value from the stack, generally speaking, is referred to as pop. So what we did a few minutes ago, it was a push. So we pushed a new value, pushed a couple of values actually in here. You saw that we pushed a couple of values, and now I want to pop these values out. So the value to be read, or the value that will be popped, and the reason why we call pop is the following. What we're going to be doing is we're going to take that value, which is 0DA23, we're going to put it in here, and I'm going to increment or decrement actually the stack pointer to the 5. So the stack pointer now refers here, and I do have that value that got popped. The reason why we call it the pop is because technically speaking, my stack doesn't know that this value here in gray exists anymore. In hardware, that value never disappeared because it's part of memory. But because my stack pointer is not referring to it anymore, and it thinks that the bottom of the stack is here, it doesn't know that this actually exists anymore. And it marks it available. So if I have a new value to be pushed, it will actually overwrite that value in gray, and so forth. So the reason why we call it pop is because we're taking it out of the stack. We're not just reading it from the stack, we're actually reading it, and we're telling the stack, hey, it doesn't exist anymore, get rid of it. Make it available. You can write over it if a new push comes in. Again, I can pop another value, and you can see that in both values, it will mark it as available, even though they're not deleted. Technically speaking, they're not deleted, but for the sake of argument, and you can virtually think about it as they're deleted, and you can see that that value, which is 1AB3, is read, and we can do something with it. For example, we can put it to the program counter and tell the program counter to go back to that particular location. And I know that my stack pointer still have some values in it, and I know that the last value that it stores in it is here. Okay, so this is what I want to cover in terms of basics of microcontrollers. What I want you to get out of it is the following. I have 3 parts, and these 3 parts are, the 3 parts that I want you to get out of it is the following. So I have memory, I have I/O and peripherals, sometimes called IOP, and I have a CPU, and they're all connected through the system bus. And most of the programs we're going to be reading, or we're going to be writing, actually controls how we get memory, how we write into memory, how we deal with the I/O, how we do certain operations within the CPU between a load or a shift register or a shifting or multiplication or addition or something like that. All right, we'll talk next time.